Cool. So I guess we will start. What's going on? My name is Dave Nufke. I teach chemistry on Long Island, and this is the math skills lab safety review portion of the program. So we're really just going to do some basic things here. A lot of this stuff is not really going to be explicitly on the exam. A lot of this stuff is going to be like the skills that you put in place in order to be able to answer questions. Some folks have filled out the form, so we got those questions and we'll put them in and we'll talk about them when we get there. I've also been through the last couple of Regents exams and I've taken out any items that are explicitly related to this material. But the lion's share of the material that we'll deal with here is not actually going to be explicit in any questions. I don't actually know if we're going to go for the whole hour or not. And if we finish early, we'll just go from there. So a couple of real quick organizational things. I really think it's important that you guys have some paper, probably your reference tables, and maybe a simple calculator can't hurt. A pen or a pencil, I suppose, is probably also something that you're going to need. You're going to want to take notes as we go through this. I really recommend that you take your notes as you go through this. You can download the slides afterwards and then compare back to the slides, but I think it's kind of silly to go through with the slides when you have them. So my advice would be to just take notes as we go through. There'll be problems embedded in the material that we're talking about. And if you get the slides early, then you'll get the solutions, which isn't really a good test for what it is that you guys are doing and what you're going to be doing in a couple of days. There's a whole bunch of information down below the video. There's a link to a Remind group if you want to send me questions there. We've noticed that the chat window, which is hilarious, is not maybe the best way to get questions to the instructors. So we're going to try this Remind group kind of thing. There's other links to other things as well. We've got a variety of resources, and of course, we've got the link to the rest of the schedule too. So you can get all of that information as you need it to kind of set you up to do what it is that you need to do to best prepare for the exam. So hopefully that's going to work for you, and we'll wrap up and I'll just point some of this stuff out at the end. I know there were some problems with the solutions video. The solutions video is now good to go. And so what we're going to do here is I'm going to share a presentation and we're going to work through that, and then we'll see where we are once that's all done. Probably pretty similar to what you guys have seen today already. So bear with me while I go into screen sharing. All right, and now let's take this full screen and let's put me over here. Oops, what happened there? Back to full screen. Sorry guys, every time I'm moving myself, so let me just move myself and stick it there. Cool, so right off the bat, we just have the review group. This is just the Remind group that you can put the information into in order to join up, and you're just going to text at mathchem to 81010. You can see that, and I don't really see that there's too much else to talk about there. So let's dig in. So here's our first reference table that we're going to talk about. It's reference table D. Reference table D has all of the units that you're going to need for the Regents exam. So it doesn't have Celsius. You will get temperatures in Celsius as well. As you guys already know, Celsius and Kelvin are very closely related. So all of the units that you're going to need for the exam are given to you on reference table D, and you're supposed to have facility with these different units. You should be familiar with them, and hopefully this is not the first time that you guys have seen any of these units. Many of the units, but not all of them, are from the metric system. So the modern variant of the metric system, which is called the international system, has 7 base units. 2 of the units that are in that system are not things that you'll see till next year, but the other 5 are units that you probably have already been exposed to and units that you guys have some familiarity with. What's cool about the metric system is that it uses a series of prefixes that represent a power of 10 either up or down from the base unit. So we put prefixes in front of our units in order to indicate the magnitude of those units. So for instance, the kilo prefix represents 1,000 of the base unit, or the pico unit represents a billionth. Is that right? No, I'm sorry, a trillionth of the base unit. Forgive me, I sometimes get my billionths and trillions mixed up. But we just use these symbols that we put in front. So we would call a kilometer a km, right? Nothing all that new there, nothing all that crazy. But you do get this table of selected prefixes. And what that really means to you is that you should be able to go from the base unit, from any of these, right, to any of their prefixed variants in order to go through all the different scales of 10. And we'll talk about conversions a little bit later. So we've already got through our reference tables D and C. I want to talk a little bit about some of these units. So it's a good idea to have a handle on which metric unit is best for what purpose. So I've got two different quantities, and I want you to take a moment and just jot down what you think the best or most appropriate unit would be to use in each of these. I'll give you guys a moment, and then we'll go through them. I'm telling you right now that the chat window is already a little bit behind where I am, so you'll forgive me if I don't reference it. If you get it right, you're awesome. We all recognize that you're awesome, but I won't be able to tell you in real time just how awesome you are, and so I apologize for that. But take a second, jot down which unit is best for what. It's just a good thing to have a handle on here as you go into you get to the final stages with the Regents exam. Cool. So the distance between your location and Philadelphia, probably the best unit there would be kilometers, which we represent as km. That's because an individual meter is not going to get you to Philadelphia, but if we start talking about thousands, units of thousands of meters, that's definitely going to be the preferred metric unit for measuring a distance like that. The mass of a glass of water is probably best done in grams, though you could probably also do it in decagrams if it's more than 10 grams, right? Then a decagram unit would be probably most appropriate. So just a good idea to have a handle on. But other than that, we're not really going to spend too much time here. Occasionally, I'm going to put in these questions, and you'll recognize them from their white background. These questions are questions that have been taken off of the last couple of Regents exams. So whenever you see one of these, and there's not going to be too many of them here in what we're doing, these questions are questions that I've taken off of the last few Regents exams. And what I'd invite you to do right now is to answer this one. The concentration of a solution can be expressed in what units? Take a moment, jot down an answer, and then we'll go through the solution together. Yeah, so it's kind of an interesting problem. If you look at the table of units, you're going to see that none of these units are on it, or at least the ones that are on it don't really address this question. So here is our reference table again, and if we go down to concentration, we see that we actually have two different units, parts per million and molarity, both of which can be used for concentration. But our answers are not giving us either parts per million or molarity. This is actually kind of an advanced question. What you're going to need to do is actually go to reference table T and get the molarity equation. Molarity is defined as moles of solute per liter of solution, and that's the key that we need. Once we know that we can do molarity as moles of solute per liter of solution, and we're talking about concentration, they're really just giving us the definition for concentration. And so the best answer here is going to be moles per liter. I hope that makes sense. If it doesn't, you can always leave your confusion in the comments and maybe somebody can help you out. But let's move on. We're going to talk a little bit now about significant figures, what I'll call sig figs, usually because I'm lazy. A significant figure is just, these are a way of indicating the accuracy and precision of a measurement. So when we talk about measurements, we want to be both accurate and precise, but it is possible to be accurate and not be precise, or precise and not accurate, or neither. And when we're recording our data, that's really where the significant figures really play in chemistry. But for reasons that we'll see when we're dealing with exams, we're going to have to deal with significant figures basically on paper. So really quickly, an accurate measurement is one that is close to the actual value of that measurement. Whereas a precise measurement is one that is made to a particular level of detail, to a particular decimal place, if you want to think about it that way, to the ones or the tens or the hundredths, right? These are all levels of precision that we can have in our measurements. We always want to be accurate and precise, but it is possible to be really precise and totally not accurate, or to be neither accurate nor precise. The bottom line is that when we're recording data, we only want to count the numbers that we should count. The ones that we have a reasonable certainty are both accurate and as precise as we can be given the limitations of our measuring device. These are the significant figures. When we're measuring a device, when we're measuring something with a device, we can only measure to the limitations of that device. The rule of thumb is to always measure to one place beyond a device's smallest markings. That's what we call the significant figures. These are the numbers that we can get out of using our measuring device and know with any certainty. What this slide is showing you is 3 different rulers. Each of these rulers is to a different level of precision. The top ruler goes to the nearest whole centimeter. The middle ruler goes to the nearest 1/10 of a centimeter, and the bottom ruler goes to the nearest 10 centimeters. So there's one flaw in this slide, which is that all of these rulers look like they're the same length. So just consider that they've been blown up to larger or smaller scales, depending upon what the scale of the ruler is telling us. And so when we measure lines or anything using these rulers, we're going to be limited in our precision. Our first ruler, it goes to the nearest whole centimeter, so we can measure and make our measurement to the nearest 1/10. I've estimated that line to be 6.2 centimeters. Our middle ruler goes to the nearest 1/10 of a centimeter, so we can make our measurement to the nearest 100th of a centimeter. I measured it to be 0.47 centimeters. And our bottom ruler goes to the nearest 10 centimeters, and so I made my measurement to the nearest 1 centimeter. In each case, I'm measuring to one place beyond a device's smallest markings. That's the only numbers that I can reasonably be able to estimate with any sort of accuracy. These are the significant figures, which are totally limited by the device. But of course, when we're measuring liquids, and this is one particular thing that's specific to liquids in tubes, because of the surface tension of water, liquids will form a curve at the top, at the interface between the atmosphere and that water. It'll be a downward facing curve. That is called the meniscus. And when we're measuring a liquid in a tube, we always want to measure from the bottom of the meniscus, or the bottom of that curve. So you can see here's a graduated cylinder. Here's an amount of liquid in that graduated cylinder. This graduated cylinder is marked off to the nearest whole centimeter. So that means that to the nearest whole milliliter. So that means that we can make our measurements to the nearest 1/10 of a milliliter. And so by looking at where that line is, we're estimating this measurement to be 21.6 milliliters. Again, we're going to the nearest, to one beyond the markings on our device, and then we're just doing our best to make that estimate as closely as possible. For the most part, when you are dealing with Regents questions, you're not actually going to be reading devices. There are a series of Regents questions that we have seen in the past where they may give you a part of a ruler and ask you to make a measurement with it. In that case, you're always going to use that rule that we go to one place beyond the markings on the device. But a lot of times what the Regents is going to do is it's just going to give you measurements, and it's going to ask you to figure out how many significant figures there are in that measurement, or after doing some amount of math with those measurements, how many significant figures there should be in our answers. For that, we use a series of significant figure rules. This is a way of, when we show you a number, we can figure out how many significant figures there are in that measurement just by looking at the measurement on the page. The rules are pretty simple. The first rule is that all non-zero numbers, so anything 1, 2, 3, 4, 5, 6, 7, 8, 9, are significant. And then numbers that do not have a decimal in them, any zeros that come at the end or to the right of the last non-zero number are not significant unless we've indicated that they are significant, usually by putting a line over the last significant zero. For numbers with a decimal, all of the zeros to the left of the first non-zero number are not significant. This is because when we're making measurements, we're going to need to indicate the place value of our particular measurement. And so if I measure something to the nearest thousands, I'm going to have a series of zeros that come after my 1 or 2 or 3 in the thousands column that I don't actually know. They're just placeholder zeros. Those are the insignificant zeros. The same thing if we're measuring things with a decimal point. That means we're going to numbers smaller than 1. And so we're going to have a series of zeros, perhaps, that are just indicating place that we do not know with certainty. And so in each case, whether there's a decimal or not, it's really the zeros that are just those placeholder zeros that are the ones that we are not concerning ourselves with. So again, numbers without a decimal, any zeros to the right of the last non-zero number are not significant. and numbers with a decimal, any zeros to the left of the first non-zero number are not significant. There are a couple of exceptions to this. It's a little bit probably beyond what you'd be asked to do on the Regents. But so for instance, if I counted the number of students in a room and I figured out that there were 36 students, that is an exact count. And that's treated as having an infinite value of an infinitely precise value. So that would not affect significant figure calculations, but you're not going to have to deal with that on the Regents exam. I've got a series of numbers here, and what I'd like you to try to do is just jot down how many significant figures they have. Once you go through that, we'll go through each one and we'll figure it out together. So take a moment and get started. Cool, so let's start going through them. 3,456 centimeters, that has 4 significant figures, and that should probably be obvious. There are no zeros here, and all non-zero numbers are significant digits. 345.6 centimeters also has 4 significant figures because, again, there are no non-zero numbers. Where it starts to get tricky is when we start to bring in zeros. So looking at C also has 4 significant figures. The reason it has 4 significant figures is because it has a decimal point present. And since there's a decimal point present in 300.0, there are no zeros to the left of or in front of that 3. And so those would be insignificant. But all of the zeros that come after that 3, because there's a decimal point present, these are significant zeros. If we didn't know that our answer was precise to the 10th place and that it was actually a 0 in that 10th place, we wouldn't have written down that 0.0. And that's what makes all of these zeros significant zeros. D has 1 significant figure. That's because we have 300, we have no decimal point present, we have no indicator that either of those zeros is in fact significant. And so in that case, only that first 3 is a significant figure. The 2 zeros that come afterwards are both not counting. Looking at E also has 1 significant figure. A decimal point is present, and we've got 2 zeros in front of our first real number, that 3. Those 2 zeros are really only indicating the place value of that 3, and so they're not counted as significant. And then F has 2 significant figures. If we didn't know that the 0 after 3 was in fact reasonably certain to be a 0, we wouldn't have written it. So the fact that we've written that 0 after that 3 makes that also a significant figure. If you guys have any questions about this, feel free to use the Remind group or any of the resources that we've linked to in order to help you get the questions answered that you need answered. Let's move on. This is a question that was submitted on our form. And the question is, do you lose credit if the significant figures are not exactly correct? For example, my answer is 44.45 milliliters, and the correct answer is actually 44.5 when you pay attention to significant figures. Will this answer count or not? The answer here is that this will only cost you credit if the question specifically mentions significant figures. But, and I can't stress this enough, it cannot hurt you to be careful in what you do. So it's not a bad idea to use your significant figure rules anyway and not worry about so much the whole issue of, am I going to lose credit or not? My advice would be just be as cautious and as careful as you can be. But at the same time, if the question does not mention significant figures, you do not have to worry about the number of significant figures. When things get tricky with significant figures, it's when we start to add, subtract, divide, and multiply numbers that use significant figures. So here are the rules for that. When we add or subtract answers, the answer can only be as precise as the least precise term. And what we mean here is more decimal places or more significant figures to the right of our answer, the more precise that term is going to be. If you think about it, if you have 2 different terms with varying levels of precision, you can only be certain that your answer is actually precise and accurate to the least precise place in your terms. The other one could be much, much more precise, but we don't know what the precision is of that previous answer in respect to all of those extra levels of decimals, all of those extra numbers. So we cannot conclude that our answer is any more precise than our least precise term. Let's do a couple of examples with this. So what I'd like you to do right now is add these 3 numbers together and write down your answer to be as precise as you think it can be. Cool. So let's take a look at what this is. So when we add those three numbers together, we're going to wind up with an answer of 42.357 centimeters. But we haven't used our significant figure rules yet. Our answer can only be as precise as the least precise term. If we look, term A is only precise to the tenths. So that means that our answer can only be precise to the tenths. So what we do is we go to our unrounded answer. We go to the tenths place. We look next door at the hundredths. It's a 5 or greater. So that means we're going to round up our tenths up 1. And the best answer we can record here is 42.4 centimeters. That is maximally precise that we can be based on our terms. Try this subtraction problem and let's see how that works. Cool, so checking this one out, right? Once we do the math, we're gonna wind up with 6,621.3 milliliters. But again, we're going to need to apply our precision rules. The first term is only precise to the hundreds place, which means that our answer can only be precise to the hundreds place as well. Looking at our unrounded answer, we have a 6 in the hundreds place. Next door in the tens, we have a 2. So that means we're just going to round that down. We're going to record that as 6,600 milliliters. This only has 2 significant figures in our answer. Let's go and talk about some multiplication and division. When we multiply or divide, the answer can only have as many significant figures as the term with the fewest. So it's not precision here that matters. Here it's just the total number of significant figures in each of our terms. Let's try a couple of different problems. Try this one on your own, and then we'll go through it together. Cool, so let's go and try this one. Once we do this multiplication, we're going to wind up with 619.584 centimeters squared. When we actually look at our significant figures, we see that our first term has 4 and our second term has 3. So our answer can only have 3 significant figures. Next door to that, 9 is a 5, so we should round that up, which makes 620, but that 0 is actually significant. So we can indicate the significance of that 0 either by putting a decimal point or by putting the line over it to indicate that we in fact know it with certainty. Try this division problem and then we'll go from there. So everybody knows 30 divided by 3 is going to be 10, right? We're going to get 10 grams per milliliter. If we look at our answers, if we look at our terms, we have 3 significant figures in our first term and 2 in our second. So that means our answer has to have 2 significant figures. We have to indicate that that 0 is in fact a significant 0. And so we do that either by putting a decimal point or by putting a line over it. Hopefully this makes sense. If it doesn't, feel free to leave your questions in the various places we have available for you to leave your questions. And I promise I will try my best to get back to you as much as I can, even if I don't get it right now. So when we're dealing with math and significant figures, you're always going to do the math first, and then you're going to look at your terms of your problem to figure out what needs to happen. And then you're going to change your answer accordingly. You may need to round your answer if necessary. It's time for another Regents question. So here we go. A sodium hydroxide solution and an acid-base indicator are used to determine the molarity of an HCl solution. A 25.0 milliliter sample of the HCl is exactly neutralized by 15.0 milliliters of 0.20 molar NaOH. Based on the data, the calculated molarity of the HCl solution should be expressed to what number of significant figures? Just to help you out, because I know that we're not really focused on acids and bases in this particular lesson, you're going to use the titration equation to do this. The titration equation is MAVA equals MBVB. That's all the help that I'm going to give you here. So try it, and then let's go through it together. All right, let's start walking through this problem together. So if we're looking at this problem, really what we want to figure out here is we want to figure out the molarity of the acid. So if we rearrange this, the molarity of the acid is going to be equal to the molarity of the base times the volume of the base divided by the volume of the acid. When we plug in our answers, it's going to look like this. It's going to be 0.20 molar times 15.0 molar divided by 25.0 molar. So in really, just looking at significant figures, we're multiplying a 2 significant figure number by a 3 significant figure number, and then we're dividing that by a 3 significant figure number. Multiplication and division, our answer can only have as many significant figures as the least in our terms. So 2 times 3 divided by 3 can only have 2 significant figures in our answer. This is a free response question on Regents exam. I don't think the most recent one, but probably the August Regents exam. And if you know your significant figure rules, this is really free and easy points. I hope that makes sense. If you guys have any questions, don't hesitate to leave them, and we'll make sure that we can get to them. Let's move on. Oh, I don't know why I did that, but there you go. Because that is determining the number of significant figures. We're going to pause here for a second, and we're going to talk about percent error. The reason why is because we've just been talking about accuracy and precision, and percent error is the main way that we quantify inaccuracy in the laboratory setting. So it's not a bad time to talk about it here. This formula is on reference table T. The percent error is just given as the measured value minus the accepted value divided by the accepted value times 100. Once we get this, we're going to get some value out of it that's going to tell us how accurate or inaccurate we are. I'm sure that you're all very familiar with the percent error formula, but let's go through and try a problem just to make sure that we all know what we're doing. So this is again off of a Regents exam. 3 elements represented by D, E, and Q are located in period 3. Some properties of these elements are listed in the table below. A student's experimental result indicates that the density of element Q is 2.10 grams per cubic centimeter at room temperature and standard pressure. Determine the percent error between the student's experimental density and the accepted density of element Q. I'll give you a moment, figure it out, and then we'll go through it together. Cool. So percent error formula, measured value minus accepted value divided by accepted value times 100. Plugging in my values, I get 2.10 grams per cubic centimeter minus 2.00 grams per cubic centimeter divided by 2.00 grams per cubic centimeter, pardon me, times 100. Substituting in my the math, I'm going to get 0.10 grams per cubic centimeter divided by 2.00 grams per cubic centimeter times 100. And when I crank that out, it's going to be 5%. It's going to be positive 5% because my measured value was greater than my accepted value. If I had measured a value that was 5% less than the accepted value, I would get a negative number out of this. I always tell my students to treat the percent error formula like an absolute value. So whether or not you get positives or negatives, it doesn't really matter. In reality, of course, a positive just means that your answer is greater than the accepted value, and a negative means that your answer is less than the accepted value. But you can leave off that positive, or if you get a negative sign out, that negative out of the problem, and you'll still get full credit for the answer. Let's move on. We're going to talk about some of the strategies that we use when dealing with really big and really small numbers, because chemistry deals with really, really big things and really, really small things. So there's like that many, you can see them on the slide, atoms of carbon in a typical pencil, and a typical carbon atom is that tiny in terms of its diameter in meters. So fantastic, you can see it here. These are huge numbers. We do not want to have to be able to deal with numbers that are this big or this small without having a way of standardizing how we write them. And so you guys all probably know where we're going. We're going to talk about scientific notation. Scientific notation is just a way that we can take really, really big numbers and really, really small numbers and write them in a standardized setting. So this hopefully makes some sense to you guys as to why we would want to deal with this, because you guys are probably all familiar with the mole at this point, which is 6.02 times 10 to the 23rd. We wouldn't want to write 602 and then 21 zeros after that every time we were going to deal with it. We would make mistakes, we would have problems, and so it would not be a fun time. So instead, we rewrite it in scientific notation. Scientific notation is always going to have a coefficient that is greater than 1 and less than 10. And in that coefficient is all of the significant figures in that measurement. And then we're going to have an exponent, a power of 10 exponent. So it's always going to be base 10 to some sort of number. Here's our mole as an example. The reason we are going to deal with this is because, or the reason we want to deal with this or do it is because it just makes life easier. Big numbers, the exponent will always be positive. So anytime I see a scientifically notated number with an exponent that's greater than 0, I know that it is a positive number. And small numbers, the exponent is always going to be negative. So anytime I see a number with an exponent that's less than 0, I know that I'm dealing with a number that's smaller than 1. Does that make sense? Hopefully it does. But the real power of scientific notation, and here's a question that came off of the Google form, right? How do you solve scientific notation problems? That feeds into how we do it. Scientific notation makes our lives easier because if we have common exponent powers of 10, when we do math with them, it's going to help us out. So when we multiply exponents, you can add them together. And so the way I've written this here is that n times 10 to the a multiplied by m times 10 to the b is going to be equal to the product of n times m. So those two coefficients multiplied by each other times 10 to the, and all we do there is just add the exponent a and the exponent b. That is super, super easy. And if we had these numbers out of scientific notation, it would not be obvious that we could even do this. If we're going to divide exponents, we're going to subtract them. So n times 10 to the a divided by m times 10 to the b is going to be equal to the product of n divided by m times 10 to the a minus b. So we're just going to, again, do the math that involves the coefficients, and then we're going to subtract our exponents, we're going to subtract b from a, which makes life, again, really, really easy. And then adding and subtracting the same exponent, you just keep that exponent. So n times 10 to the a plus m times 10 to the a is going to be equal to n plus m, and then just times 10 to the a. It just remains intact. You do not have to change it. But notice there, particularly, they have to be the same exponent in order to work. Let's go through and let's look at a couple of different examples of how this works. So with multiplication and division, you're always going to do the coefficient math first, any significant figure rounding you might need to do, and then deal with the exponent after the fact with the adjustment. Let's go and take a look. Try this example on your own, and then we'll go through it together, and we'll see how we do it. So I noticed that some of you guys are coming through on the remind, and that's cool. I'm obviously will definitely find some time to make sure that you guys get all of your questions answered that are on the remind, whether it happens online or not. We'll figure it out. But like Kira, I got you. I just can't get you just yet. Would it be okay to leave on there? Yeah, Kira, you totally should be able to get the same answer. But my advice to you would be to try it and do it, and then we'll kind of see what goes from there. Let's look at this equation and see how it works out. So 4.70 times 7.3, we're going to do that math, and then it's going to be times 10 to the 5 plus negative 3. Working this through, it's going to be 34.31. That's 4.70 times 7.3 times 10 to the second. 5 plus negative 3 is 2. I'm looking at this answer. It really needs to be in scientific notation. 7.3 only has 2 significant figures, so that's going to be 34. And then if I really want to put it in actual true scientific notation, 3.4 times 10 to the third. Let's be very clear here. I would only have to do these last steps if the question was specifically asking me to make sure that my answer had the correct number of significant figures and was in scientific notation. You're never going to be asked to do that on the Regents exam altogether, but it is something you should be aware of, particularly here as we're practicing. We'd rather you be over-practiced than under-practiced. Let's look at the next example. This is going to deal with addition and subtraction. So with addition and subtraction, always adjust the exponents first. Remember, they need to have the same exponent in order for that exponent math to remain. And then do the math that involves the adjusted coefficients. And that, of course, is going to deal with your significant figure rounding and your scientific notation as well. So try this example, and then we will look at it together. All right, so we have to adjust an exponent first, and it really doesn't matter which one we're going to adjust, but I'll usually take the bigger one and make it smaller. So what I've done is I've adjusted that second term. 4.6 times 10 to the 8th is 46 times 10 to the 7th. The way that I work my way through adjusting the exponent and the coefficient is I figure out it's like a seesaw. I made 4.6, I'm sorry, I had to take 10.8 and bring it down a power of 10. That means that I had to take my coefficient and bring it up by a power of 10. Since 10 to the 8 went down to 10 to the 7, that means that 4.6 has to go up 1 power of 10 to 46. Once that's done, I can now do the math I need to do. 5.6 plus 46 will let me 10 times 10 to the 7. 5.6 plus 46 is 51.6 times 10 to the 7. And of course, I need to round that off to 52 times 10 to the 7, since 46 is only precise to the ones place. Does that make sense? Again, you're not going to be required to do both rounding, significant figures, and scientific notation all together in a problem, but it's a good idea to look at these examples and try them that way. Oh, I'm sorry. And then, of course, I put it back into scientific notation. And by putting it back into scientific notation, I then was able to actually have it in true scientific notation. So you can see that even I will sometimes confuse myself and figure that I'm done before I'm all the way done when we're asked to do all of these different things. I got a question about, are we going to review all of the table T equations? I believe that all of the different table T equations are being reviewed at different points over the course of these sessions. If we have some time at the end, I can definitely throw up table T and we can take a look at it and see what's going on. But I don't know if we're going to have enough time or not. Let's move on. Let's talk about unit conversions. So for converting between units, there are obviously a lot of different kinds of units, and you need to be able to move between them pretty easily. A lot of us have learned something like King Henry does bake delicious chocolate muffins to go from kilo 10 to the third down to milli 10 to the negative third using the decimal slide, right? However many steps you're doing, you're going to move your decimal to the right or to the left that many number of times. You will probably not be able to do that if you're asked to convert on the Regents exam. They're probably going to give you something outside of decimal slide territory. And if that's the case, you're going to need to be able to use a different way of converting, what we call dimensional analysis. And that's the method that I'm going to show you guys here. You guys have probably talked about that in your own classes. Let's talk about some things that you can't convert between. So you can't convert between units that measure different properties. So like if you were asked to convert 12 seconds into meters, you couldn't do that because meters measure length and seconds measure time. So that's not going to work for us. At the same time, you can combine units into what we call a complex unit. So for instance, 5 milliliters of a substance has a mass of 12 grams. What's its density? For that, we're going to divide 12 grams by 3 milliliters. That's going to give us 4 grams per milliliter. Notice that I've just taken my two units and I've combined them, expressing their mathematical relationship between each other. That's how we've gotten that. That's totally allowed, totally fine. But we can't convert from grams to milliliters because we're measuring two different quantities of a substance. When we're in chemistry, you really want to convert using conversion factors through what we call dimensional analysis. So what you do in this case is you're given a quantity and you multiply it by a conversion factor, which is a parentheses with a relationship between the unit that you are converting out of, or the unit you're converting from on the bottom, to the unit you're converting into, or the unit you're converting to on the top. These two things in the conversion factor are equivalent. So it would be whatever unit you're coming from and whatever unit you're going to, equivalent amounts of both. Generally speaking, when you're converting, you don't gain or lose precision in your answers, but you guys don't really need to worry about that here in Regents Crunch Time. So how do you convert between units? You're really going to use reference table C here and common sense, at least when we're talking about the metric system. You can also use dimensional analysis for converting outside of the metric system. Many of you have probably used it to convert between like atmospheres and kilopascals for the purpose of pressure conversions. But so anyway, let's go in and let's take a look at how this works. Try this one on your own and then we'll figure it out together. How many millimeters are there in 630 kilometers? Give it a shot and then let's go through it together. All right, let's take a look and let's see how this works. This is my conversion right here. So what I've done is I've just put table C up so you can see it. I've circled the factors that I'm going to use. So I'm going to write down my quantity that I have, 630 kilometers, and we know that that zero is a significant zero. And then I'm going to convert. So my conversion factor has kilometers on the bottom and millimeters on the top. Which one is bigger? Kilometers. The factor for kilometer is 10 to the third. So I make that equal to 1. And then up at the top, how many millimeters are there in a kilometer? Well, if we notice, kilo is 10 to the third and milli is 10 to the negative third, that means that there's 10 to the sixth difference between them. In other words, 1 kilometer is going to be 10 to the sixth, or 1 million millimeters. So that's what I have up at the top, 1 million millimeters. I could have easily written that as 10 to the sixth, and it would all work out fine as well. When I do this, my final answer is going to wind up being 630 million millimeters, with that 0 after the 3 and 630 significant, which is why I put the line over it to indicate that I, in fact, do know that it is a significant 0. But if you didn't have that and you weren't asked to make sure that you had significant figures, it would not matter, as I'm sure you guys have probably picked up from this point already. Let's try another one, shall we? Oh, this is just that number written in scientific notation, in case I were for some reason asked to do so. It's 6.30 times 10 to the sixth millimeters. It occurs to me that that is not correct. It is 6.30 times 10 to the eighth millimeters. I apologize. Looking at the next one, try this one on your own, and we'll go from small to big, and we'll figure that one out. So 12 micrograms is equal to how many centigrams? Give it a shot, try it out, and then let's go through it together. Cool, so again, here's my conversion. I'm going 12 micrograms. Notice that the unit for micro is this weird thing that looks like a U. It's actually a mu. You don't need to worry too much about it. You just need to know how to draw it and recognize it when you see it. So I've got 12 micrograms. I'm going to centigrams. The factor for micro is 10 to the negative 6, and the factor for centi is 10 to the negative second. So we know that centi is bigger. So I've got 1 centigram at the top of my conversion factor. And then how many micrograms are there in a centigram? Well, there's what? There's got to be 10 to the 4, or 10,000 micrograms in a centigram. So when I do this math, I'm going to wind up with 0.0012 centigrams, which is the correct answer for this problem. Does that make sense? I hope it does. If you guys have any questions, don't hesitate to ask. Putting it in scientific notation, we get 1.2 times 10 to the negative third centigrams. Cool. So that's conversions. We can, of course, convert between anything. We don't need to stay in the metric system. As long as we know what the equivalency is in that conversion factor, and we always put the unit we're going from on the bottom and the unit we're going to on the top, we can convert until the cows come home. And even then, we can probably convert the cows. So let's move on. We're going to talk a little bit about graphing here, all right? When we're graphing things, we're always interested in our different variables. So the independent variable is usually the experiment that the condition of the experiment that the experimenter allows to change, and then the dependent variable is the one that changes as a result. When we're constructing a graph, we're going to need to have the following items in a graph, and you will most likely have to create a graph on the Regents exam. So you're going to have your x and y axes. The independent variable is on the x-axis with units. The dependent variable is on the y-axis with units. You're going to need some sort of scale. You definitely want to make sure that you have uniform increases in each variable when you're scaling your axes. You do not have to start your axis at 0 if you do not have 0 data. You can start at the lowest value that enables you to scale your axis correctly. That is totally fine, but then you would make sure that you put that lowest value down at the bottom. You would not have a 0 first, unless you're going to break the graph, which is allowed, but I usually do not recommend it because kids usually find it to be a little bit strange. All right, so we're going to scale our axes this way. You may need a title, though usually the Regents doesn't ask you for a title. I usually like things like dependent variable versus independent variable, for instance, tends to work. They're going to ask you to circle your points when you plot your points, you definitely want to do that. If you have to plot multiple values simultaneously, you're going to use different kinds of circles, or like triangles or squares for different series of points with a key. It's going to tell you to do that when you do it. I've gotten a question in that asks, will you lose points if you don't label your axes when graphing? Yeah, probably. Your axes will probably actually already be labeled for you. Most of the graphs that we get already have them labeled, but you definitely should label your axes if you get an unlabeled axis, totally. When we connect our data points, right, you're just going to connect them with a straight line. I have yet to see any sort of instruction to do a best fit on the Regents, but you would only do a best fit if you were asked to. Please, otherwise, just go like we have in the middle here. Just connect the lines as neatly as you can, connect the points. So yeah, don't leave them unconnected unless you are specifically asked to not connect them. You might probably have to read data off of it. If you're reading data from within the series of plotted points, that's called an interpolation. If you're reading data from outside, that's called an extrapolation. And you may be asked to describe the relationship between the variables. If you have a situation where as one variable goes up, the other goes up, which also means that as one goes down, the other goes down, that is called a direct relationship. You can either say as x increases, y increases, or vice versa, or you can just say there is a direct relationship between x and y. The other relationship that we see in chemistry, for the most part, is the inverse relationship, whereas one goes up, the other goes down in a particular relationship, so that when one is doubled, the other is halved. When one is multiplied by 4, the other is quartered. You get a curve for an inverse relationship. And again, you can say as one goes up, the other goes down, or you can say there's an inverse relationship between x and y. Either will be fine. You are usually asked to express the relationship between two variables in a graph, in a graphing series of questions. So it's a good idea to have a handle on these. We're now going to go back in, we're kind of moving towards the lab already. We're just going to talk about some of the lab tools that you should have some familiarity with. It's been a while since we've seen a question that deals with a particular tool for a particular purpose. At the same time, it's a good idea to have a handle on many of the tools that you've seen in the chemistry lab. So these are beakers. They're used to hold liquids. You may have held other things in them as well. They're basically the glass of the laboratory world. If you just need to put a liquid in something, usually you're going to put it in a beaker. You may also have put liquids in flasks as well. There are different kinds of flasks. This flask is called an Erlenmeyer flask. You don't need to worry about that particularly for the purpose of this exam, but at the same time, it is another place where we often put liquids. Beakers and flasks both have markings on the side to indicate the scale of the liquid that's in them, but these are not precise markings at all. You would never want to measure volume of a liquid using a beaker or a flask. For that, you would want a device that is actually much more precise in terms of its measurements. That would be something like a graduated cylinder. So you guys have seen plenty of graduated cylinders before. You only measure volumes in the lab usually of liquids by using a graduated cylinder, right? So here it's measuring liquids, it's not just holding the liquids. And notice that we have progressively finer gradations on these different types of graduated cylinders. Or you could also measure a liquid using a burette, which is probably something that you have all done when you did acid and base chemistry, or at least your teacher showed you. With burettes, we should talk quickly about how we measured the volume in a burette. It is not unheard of to be asked to read a burette. You know, they'll give you a picture on the exam and ask you to read the volume. You read it from the top down. So that's particularly bizarre because usually when you're measuring with a graduated cylinder, you're going to read from the bottom up. So for instance, we would read the volume of liquid in this burette currently as what, 20.95 milliliters, something like that. And that's again, bottom of the meniscus, one estimation past the measuring scale of the device, right? So we see that this is going to every 1/10 of a milliliter. We go one place beyond it. So I'm going to call this 20.95. And then we would let some liquid out, and then we would read it again, and we could figure out the change in the amount of the liquid. Cool? Kind of weird, so I figured we would talk about it here. There are other lab tools as well that you're probably very familiar with. This is a triple beam balance. I don't know if you use them or not. Some teachers only use electronic balances these days. If you're going to use a triple beam balance, you're going to get the weight off of that balance by reading the sliders on the balance once the item has been totally balanced. And you can get a very precise reading off of a triple beam balance. This triple beam balance, for instance, would give you readings to the nearest hundredth of a gram, because it goes to individual grams and then the markings are the nearest tenth of a gram. So we can go one place beyond that to get to the nearest hundredth of a gram, which is pretty cool. Of course, if you had an electronic balance, we would just read it off the device. We wouldn't make any estimations beyond that. This, of course, classic chemistry piece of lab equipment. This is a Bunsen burner that's used for heating materials. When we use a Bunsen burner, we're going to get a flame that comes out of it. It burns essentially methane or propane that comes out of the vents, probably propane, because otherwise it would stink. And so these are different types of Bunsen burner flames. Really, the best flame that we see here is the one that is indicated with the big red arrow pointing to it. The hottest part of the Bunsen burner flame is the inner part, is the top of the inner flame. The inner flame is called the cone, and so the tip of the cone is where things are the hottest. There can be a great variable in temperature in a Bunsen burner flame, maybe even as much as a couple hundred degrees, depending upon whether you're at the top of both flames or if you're at the tip of the cone. Bunsen burner flames are incredibly hot. You can easily melt glass with Bunsen burner flames. So it is something that you probably all have some experience with and are probably somewhat scared of, at least if you're kind of like my students. In terms of heating things up, we can heat things up directly or we can heat them up indirectly. A crucible, which many of you probably have used in your chemistry classes, is used to heat stuff up directly. It's made out of ceramic, and so it can be heated much, much hotter than even the hottest Bunsen burner flame without melting. No joke. I mean, it will look like the space shuttle re-entering the atmosphere, but it will not break when you heat it up that much. And so you can heat things up incredibly hot in a crucible just by torching the bottom directly using a Bunsen burner flame. A lot of other times you might need to use apparatus and arrange that apparatus in order to get things to work correctly. So for instance, here we see a typical laboratory technique that I'm sure almost everybody in Regents chemistry has dealt with over the course of the year, and that's for heating a liquid. For that, we are going to use a Bunsen burner and a ring stand. And then we're going to put an iron ring on that ring stand. We're going to put wire gauze on top of that iron ring, and then the beaker on top of the wire gauze. The wire gauze will have a coating of asbestos on it, not the kind that's going to hurt you. Asbestos will distribute the heat more evenly. And so if you were to heat a beaker bottom with a Bunsen burner directly, that would not work out so well for you. The beaker would essentially melt and crack. And so in order to heat it using a Bunsen burner flame, you would use an apparatus like this to distribute the heat and keep it from basically breaking and melting in your face, which is not a good idea. This is another lab technique that you've probably seen. This is for distillation. So in this situation here, we're using a hot plate instead of a Bunsen burner. We've got a thermometer to indicate the temperature. We've got a device called a condenser, which is shown here as in 5. And then we've got 2 different flasks. We're heating the flask in 15. As that gets heated, different liquids in that mixture have different boiling points. Once we get to the boiling point of the first liquid, that starts to evaporate out. That vapor then goes and is driven into the condenser. The condenser uses cooled water to lower the temperature of that vapor and cause it to condense, to liquefy. It will then run down into flask 8. And so we can collect the different components of the mixture by using the distillation apparatus. As long as we keep the cold water running, this will continue to work. And you have probably seen that in your own class. And then, of course, we have titration using burettes and flasks. So in a titration, we've got our burettes and our flasks, and we can control the amount of liquid that we're putting in as indicated by different color changes. These are not the only 3 situations that you might see, but these are the major 3 kinds of chemistry situations that you've probably dealt with in the lab. And these are the ones that you should be probably most familiar with for the purpose of the exam. To wrap up, we're just going to talk about some laboratory safety. So my personal favorite instruction is always follow directions, right? Just listen to what your teacher is telling you and do what your teacher asks you to do. If you have questions, ask if you're confused. You certainly want to wear gloves and goggles and apron, appropriate clothing, tie back the hair, no closed-toed shoes. You don't want to eat or drink anything in the lab. And if you're instructed to smell a chemical, you want to waft it towards your nose to smell it. You don't want to put your honker over the thing and just take a big snort, right? You want to just waft it like such. You want to dispose of waste safely according to the instructions. So definitely ask your teacher, don't just pour stuff down the sink. If an accident happens, you definitely want to tell your teacher. You never want to fool around. You always want to pay attention to what you're doing. There are 2 other things that we should be particularly careful of here. If you're asked to add an acid to water, You want to add the acid to the water, never the water to the acid. That is the way that you want to do it. So make sure that you follow those instructions. Otherwise, you could get in a situation where the acid basically boils and splatters in your face, and that is not a good idea. You also want to heat things without covers or stoppers, and you want them pointing away from you and, of course, from all of your lab partners as well. You don't want it pointed towards you while you're heating it, because then, of course, liquid could exit out of whatever it is that you're holding and could wind up getting all over you, or certainly get all over your partners or so on. If you heat something with a cover, of course, the pressure could build up to the point where it could explode. And so this is one last question here about laboratories. The laboratory process in which the volume of a solution of known concentration is used to determine the concentration of another solution. Is that distillation? No. Right? Fermentation, of course, is just an organic chemical reaction. Transmutation is a nuclear reaction. The correct answer for this question is, in fact, titration. And so that's what we would put for this. This is, again, off of one of the most recent Regents exams. So that, my friends, I believe is the end of our presentation. Let me go back to my ugly mug, and we'll just send you off to our next session in a second. So hold on one second. I'm going to stop screen sharing. Hey, so good job. You made it through the math review and the lab review. Awesome. I noticed that I got one last question here from Annalisa. Do we need to know about chromatography? Yeah, you probably should. It's a way of separating out the components of a mixture. You did it in a living environment when you did the lab with Botanicurus and the different species. But you can definitely go to YouTube right now and just type in like chromatography or water marker chromatography, and you'll see some examples of separating out the pigments in the ink by dissolving them all in a medium and then allowing them to separate out over a particular surface, usually a piece of paper. So I would definitely check it out. It's just another way of separating out mixtures, so it's not a bad idea to have a good handle on that. Just as a reminder, guys, you are going to have all the other sessions. The links are below me in the information form, so definitely go there to check them out. And also, I put a bunch of other links down there as well, particularly related to our stuff. You can get links to my unit on sort of the math and nature of science stuff. You can get links to crash course lab safety video. And the links to my unit also go to my website. You can always get links to any other videos for the entirety of the year. So help yourself, certainly, and good luck. I'll be pulling for you. And thanks so much, guys. I hope you enjoy the next session. Have a great day, and enjoy.